Okay. We'll do diffusion. We'll just do the introduction to diffusion, right? Mostly pictures, and there's some math here. But we'll come back after lunch when you're really ready for math. We'll do the math then. So, hey, are we recording?
Yes.
Yeah. So guys, this was VAE. We had an encoder, we had a Z space, latent space, and we had a decoder. I hope you see that the VAE can be drawn in that way, like a state transition, where you go from X to Z using an encoder, and you learn QZ given X. And then from the Z space, you use a decoder, and you learn PX given Z. Right? This is what we had done. Because remember, the encoder was learning Q Z given X, and the decoder was learning P X given Z. This is like saying, learn the rules. And this is like saying, given the rules, learn the images. Good. Diffusion would say, let's make this hierarchical. So instead of learning one rule space, let's learn this. So I will learn some rule from the image. I'll call that rule C1. And for that rule, this is also some n-dimensional space, right? So you can think of those rules as point in some n-dimensional space. And for those, I'll learn another set of rules. So this is like rules of rules, and so on. And I'll go all the way to some capital T. And then, so the encoder will now be layers of encoding. And the decoder will start from this capital ZT, the Tth rule. And we'll keep coming back, and hopefully we'll come back to that image. This is the high-level point about diffusion. So someone can say, what is the difference with VAE and this? Of course, it's now hierarchical, that's all, right? But unlike VAEs, there are some things we want to constrain, so we have better mathematical help. And these will be called variational diffusion models. Some similar to hierarchical, but we'll call it variational diffusion models. And let's see what the constraints are. These are three constraints on VAEs. Constraint number one, the latent dimension is going to be the same size as the data dimension. The rules are not now going to be some 128 dimensional space. If the image is 4,000 dimensions, rule is also 4,000 dimensions. That's the first change. Okay, so that's the first change. All these Z's has now become X. Do you see that? Earlier it was Z's. This was Z. Z typically means latent. X means the same space as image space, but it's some other rule space that has the same dimension as image. So now I'm saying, hey, learn the rules that you want in 4,000 dimensions. That's much more flexibility in the rule space. Right? And you keep doing that. So every rule is also the same dimension. That's number one. Number two, earlier, this image to rule was being learned by an encoder. Now I'm going to say there is no encoder. I'm going to come up with a function which essentially says noisify the image. So I take an image, go through the first phase of encoding. Sure, I'll take that image, I'll sprinkle noise in it, and I'll get a noisified image. That is my rule. And then in the second encoding process, I'll take that image, which is, let's say, this, and I'll put more noise. So this whole process is basically taking an image and inserting more and more and more and more noise, so that at the end, it becomes complete noise. This is the process. And the third rule that we are going to impose is the final rule, the final X capital T, that should become an isotropic Gaussian, complete white noise. So what are we saying, guys? We're saying apply a bunch of rules, apply a bunch of encoding transformations so that each of the rules becomes noisier and noisier versions of the original image, and make sure you you design the noise in such a way so that after the Tth encoding, the rule is completely white noise. This is the 3 restrictions we are imposing. And then we will sample from this xt. What is the distribution of this? Isotropic Gaussian, N01. So then the decoder, we will tell the decoder, I'll take a sample from that xt. Let's say I take this sample. That's a noise. And I ask it to now denoise slowly. And I'll train the decoder so that ultimately, when it comes over here, it exactly creates this picture. So in other words, what I'm saying is, I have some data. I'm destroying the structure of the data by adding noise. And I'm telling the decoder, hey, can you learn how to regain that structure of that data? If you learn to do this, if you've learned, I show you millions of examples and you learn how to regain structure, denoise. Once you're trained, then I can give you some random sample from Gaussian. And because you've trained to denoise, you should be able to come back to some real picture. That's kind of the high level equation. Okay. So we will train with a whole bunch of data. This will be Markovian. We'll add noise step by step. And at every step, we'll add noise only based on the previous step and we'll forget the past. And then the decoders will denoise step by step to get to the original. And imagine you've now trained this whole model. And now you sample a new random image from this xt distribution, which is a Gaussian. And let's say this noise that you sample over here is this. You give it to the decoder. The decoder is going to do something. It's going to denoise. Again, you give this one to the decoder. This decoder. It'll denoise, it'll denoise, it'll denoise. And the hope is the decoder will generate a new image. That's the hope. Thermodynamics perspective. This is what the Stanford paper does. This is the original diffusion Stanford paper from 2015. That same intuition we talked about. I put a ink in a glass of water, and I learn the process of diffusion so that it becomes blue water. Right? And now I'd say, hey, decoder, you have this blue water. Can you undo the process of chemical diffusion and come back to the point where the ink was dropped? So if I drop inks at different positions and I train it, the model might learn the actual equations of thermodynamics. And if it learns the actual equations of thermodynamics, actual equations of solubility, that's typically a differential equation. Then you can go backwards in the differential equation and give it a red water and use that same learning and come back to a point where the red ink was dropped. This is the high level equation.
Intermediate steps equidistant, like the amount of noise that we have in step.
It's not equidistant. We are going to only design the noise so that after capital T steps, that image becomes white noise. That's the only restriction we have. So we have to design the schedule of adding noise. But the schedule, if I give you capital T, that schedule is a deterministic schedule. Last and most intuitive way, in my opinion, to look at diffusion. You take an image of this hut and you destroy. It turns out, this is something that I want you to pay attention. It turns out that when you sprinkle noise on that image, initially the perceptual functions, the perceptual details of the image get lost, and the semantic details of the image get lost later. Let me say what that means. If you have a picture of a soccer ball, if you put noise into that picture, after a while, you will still say this is a ball, but I don't know what the pattern on the ball is. You keep adding noise, later the structure of the ball, which is a circle, that will die. that will go over. Okay. So in some sense, you are destroying structure, first the perceptual structures and later the semantic structures, which are the core shapes, the basis on which the ball was, that picture was made. Okay? That's the process that's happening. So now, hey, these images, these noisified images are also points in 4,000 dimensional space, right? So you can think of this destruction process as walking along some path. Agree? Right? Along this path, the image is getting destroyed. Destroyed, 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 and it eventually becomes isotropic Gaussian. Okay? But now look, if I have learned to denoise, right? Then there might be another image, which is this image, which if you start destroying, initially this image looks very different, but after some point, this destroyed heavily and this destroyed heavily might start looking similar. You see that? They have to look similar because, of course, they will look similar at the end because it's white Gaussian noise, so they have to be similar. But if these two are similar in some semantic space, they will merge halfway somewhere. So if you learn the denoiser will say, okay, if I go from here, I might go here and I get a real image. I might go here and I get another real image. So the denoiser learns at many of these 4 points which direction to go to get to the real image. 1 second, Scott. Just hold on. But this is hard because this is in 4,000 dimensional space. So in 4,000 dimensional space, imagine you're standing at this location, right? Among the 4,000 dimensions you can go to, one path will take you to the hut. One path will take you to this volcano, right? But because you've trained on these, you have an idea, looking at this kind of a picture, which direction I should go that will take me to a real image. And I go in that direction, right? So sometimes I'll go in this direction, sometimes I'll go here, but sometimes I might go here, which will also take me to a real image if I've learned the patterns well, right? But if I go in a wrong direction, I'll get noise. So can I train that guy to only follow the right paths and not go down the wrong paths?
I think you answered it. Basically, the reason that you will end up with some real image is because the training is reinforcing that which ones are
Absolutely. Absolutely.
That's why
Absolutely.
you don't end up in
Exactly.
Why maximize again the intersection of images?
No, I'm not going to do any of that. Because I have this intuition that all images, if you noisify enough, they'll be identical. All of us, if we go back in time, we are all embryos, right? So it's only character has developed over time, right? So the point is you're learning what you're destroying them, but at some point, this image and this image would have correlation in some noise space. Some noisy image captures patterns of this image and that image. That's the 4th point.
Trying to understand why this noise function is guaranteed to have long paths.
Huh. You see, right? These two.
Guaranteed on the diagram.
Over here, when these pictures come, they will all be in some very small space.
What is the actual intersection about each one of the points in the things?
Sorry.
What if the intersection, the actual intersection only exists the real noise field? Like
it's all rooted in the last image.
like
All rooted in the last image.
what guarantees that there are branches before that last image? That's my question.
Because when these two images get destroyed, it cannot be that before the destruction they're far away, but only at the last step they become same.
I might be like information about is there a mathematical.
Totally mathematical. Totally.
I guess there is some variance, so there's always close enough.
Yeah, this
Like
yeah.
there's 0, 1. This is like
This is a distribution. It's not like one image. So there is a small circular isotropic space ball in which they're all coming together. So in that there is similarity. And of course, you can go to other. So this picture and this picture might actually merge much further, much deeper. Right? This is like saying I give you a picture, and I say, can you transform this picture into some other picture? I give you a picture, right? I give you this picture, and I say, can you transform it into this picture? The question is, how much do you need to destroy in this picture before you can start going towards that picture? Right? So maybe if you destroy this part, you've gone backwards enough, and then if you start adding a triangle, you get to this picture. Whereas if I give you something very different, and I ask you to come from this picture to this picture, maybe you have to go all the way back and erase everything and then start with this picture. Right? So there is commonality, there is pattern in pictures, and I want to learn that pattern. Very good. And now I can even put probabilities on this, because as I destroy the picture, my probability of that picture is going down. Right? And as I take a fork and come to this picture, my probability is going up. Right? So you see, now because I have control on how I'm destroying the picture, I have some control on how the probability should go down. Right? And if I know that, then I want to fit a function to the images and the noisified version of the images. Okay? Noisified version. And now recall what we talked about when we said Langevin. Langevin said, if you give me score function, which is grad x log of fx, right? That score function is basically a denoiser, right? So if I do Langevin on this, it's like I am climbing on this terrain, and I've created this terrain by noisifying, destroying the structure of the image. Okay? So I want to create a full space in which every image is like a pole, and I want to create noisified images paths all the way to N01. And from that, I want to learn the mountain range, the terrain. Right? And if I've learned that, denoiser is the score. And if I use the denoiser now as a score function, I can do gradient descent. And using Langevin, I can get samples from this distribution. Samples from this distribution is what I want, because at the end of the day, I want samples from PDX.
So in Langevin picture, you had these different variances. So you had like a small, bigger. So this corresponds to different layers of the chain.
Absolutely. Absolutely. Every layer is increasing the variance. Absolutely. So if you did only a few layers, then you do not know what the picture would. Suppose this is the picture and you do few layers, then the variance, you know what the distribution looks like here, but you don't know what it's here. So you have to keep increasing the variance to make sure you cover the whole space. And then when you start doing gradient descent, wherever you start, you have a gradient and you follow the gradient.
But in Langevin itself, you didn't have to do it in steps. You could just draw a big distribution, right? At least you have to.
But then your MMSE estimator, Ex given Y, is going to screw up. Right? Even though if you put a big distribution, you have to still compute Ex given Y, right? So it's like saying, I am at DC, where did I come from? If you say you only came from a small radius, I have a much better estimate. Then you can come from anywhere in the world. It's much harder. Your estimate is going to be bad. Even though that's the optimal, it's going to be bad. Good. So what we are essentially going to do is we had that hierarchical VAE, right? We are going to compute the new ELBO. What was ELBO? The lower bound on PDX, right? That was the ELBO. So we are now asking, hey, that PDX is now like this Now a more complicated model, can I compute the lower bound of that hierarchical VAE? So this is, can we derive the more complicated ELBO? This is what the math looks like. It's actually super simple. This is not difficult at all. Okay? And this is the paper from which, this is a beautiful tutorial on understanding diffusion models, and we take the math from there. It is not, if you've gone through the cheat sheet, this is breeze, just looks scary. And part of the reason I want to go through the math slowly is because I want to show that many of these things look scary, but they're absolutely not. And I think that's the reason to actually get into these fields and play with these toys. It does not look, it is not as scary as much as it looks. So the high level goal would be, we would like to estimate a new ELBO for this variational diffusion model. We did the ELBO for one step. We'll do it for variational, and we'll say it's actually possible to do. And once we have the new ELBO, things will become very easy. So post lunch, the goal is to update that ELBO to variational ELBO. Please don't, I mean, you might think that this is not of interest to me. My feeling is, once you see that it's super easy, it'll become of interest to you. Okay? So see if you want to come back, that's all. And then it's again going to be on pictures. Oh, sorry, no, it's okay. It's not, but it's easy. Okay, so I think we'll break for lunch, but that's the intuition of diffusion, and we'll again connect all of this to the higher level intuition. But the big goal is big space, 4,000 dimension is one image manifold. Can I climb to the top of the image manifold? Good lunch.
When are we coming back? I think we have a call. We're announcing we're coming back.
1 hour.
2 p.m.
Yeah. Let's meet at 2 p.m.
2 p.m. Yeah. Online audience, we will come back at 2 p.m.
Let me quickly show you the derivation for ELBO. ELBO is evidence lower bound. What is evidence? What is this a lower bound for? I know this is after lunch, so maybe chat, right? You can turn down the lights. So let's chat a little bit. Evidence ELBO, ELBO is evidence lower bound. What is it a lower bound for? The
Reconstruction.
True. It is a lower bound for what expression? The probability density function. Okay. The distribution that we want to fit to the data, evidence lower bound is a lower bound for that. Okay. So let's quickly look at the derivation of that. Thank you so much, Mozilla. We just started, so we didn't do anything. Okay, so we are interested in PDX, correct? But in many places we do log of things. Why? Because this X, when it becomes all the data points, all the images, that X becomes X1 to N images, right? And we want to basically maximize the likelihood of the product of all the individual likelihoods. So remember, if we remember from likelihood, we did 1 to n p xi given theta. This is what we did for likelihood. Remember, this is L theta. So these are the products of the probabilities. If you take log, all those become sums. That's why it's good to take log. Right? The log of this product, log of AB equals log A plus log B. Right? So good to take log. So we always care about log PDX. Good. So now let's look at the math quickly.
Do you want to talk about constant as well? Let's also.
Okay. Let's finish this. Guys, what is this called? Marginalization. Why? Because you've introduced a new variable Z and you're integrating over all the Z's. This is like saying probability of A equals sum of probability of A comma B over all B. This is marginalization, right? Cool. So we marginalize and we write this. Now, if you have PXZ, what is this? You apply Bayes rule. PAB is PA given B times PB, Bayes rule. So you get that. Now, this is what is called variational. Actually, mathematically, variational autoencoder comes from this idea of variational. Look, I'm going to multiply this QZ given X top in the denominator and numerator. This is 1, but I have this. I can multiply. Okay. So now, over here, I take these 3 terms and I put it over here. And I take the QZ given X out. You see that? Good. Do you see this as an expectation? Why? Why is this an expectation? Okay, let's look at expectation. Expectation of X equals X fx dx. Do you agree? Very good. Now I write this as integral X fx. Sorry. And I write gx by gx. I can write it like that, right? Like gx by gx cancels off. Now I write this as integral X fx divided by gx times gx dx. Right? If gx is a distribution, then this is the expectation of this function of random variable multiplied by this distribution. Is that clear? Lotus, do you remember Lotus? Law of the unconscious statistician, right? You know the expectation of X. If you want to find the expectation of some function of the random variable gx, you just plug the function there. So this can be thought of as expectation. This is important, where X is sampled from gx. The expectation is of X of fx by gx. Right? Similarly, if you look at this one, this can be thought of as expectation X sampled from fx X. If you understand this, the bottom one is trivial. This you understand, right? If I ask you to compute the expectation of X, right? And X has a distribution fx. You can sample from that fx, and all the samples you add up and you average. That's your expectation. So this is in plain English saying, take samples from fx and add those, take an average of those samples. This is the same thing. This is the same thing. Take samples from gx and add up the function of that random variable X. Please ask questions.
So you haven't really used that. Just
I don't have it, absolutely.
Just reorganize it.
I just reorganized it in an expectation form.
So now your distribution is Q of that given X and the expectation.
The distribution now I have is Q of Z given X. This is a distribution because I designed it to be a distribution when I multiplied the numerator denominator. Very good. Okay. So I'll use that later. Now, there's something called Jensen's inequality, which says log of an expectation is greater than the expectation of the log. In fact, it doesn't have to be log. Any concave function, if you apply a concave function on an expectation, that is greater than the expectation of the concave function, and log is a concave. So you see this, we can rewrite as this. Greater than or equal. Right? This is called Jensen's inequality.
And the conditions of the Q, like is it C given that?
Oh, you're right.
You have a key to my office? I locked myself out.
1 second, someone online, just give me a second. Yes, say that again.
I'll walk first.
That's fine. I'll come. The microphone is. Thank you for the catch. QZ given X both.
Take a shortcut.
Online, can you please mute your microphone, please? Thank you. So now do you see this is the expectation. I see some rounds. Good. I'm sampling Z values from this distribution. And I'm plugging those Z values here, here, here. And I get the expectation. Good. Now I break this up. X given Z comes out here. It's log, right? So I can write that as sum. So X given Z comes out here. And the rest of it is this. Cool. This is KL divergence. This is saying make the distribution PZ and QZ given X similar. So this is basically the, this is basically the reconstruction. This is the KL divergence that we saw previously in VAE. You're telling the VAE, minimize your reconstruction error, which is this. And you're telling the VAE, make sure that the big mountain subsumes all the small mountains, which is this KL divergence. And this is the ELBO. Okay. Does that make sense? This is the lower bound of how well you can fit the data.
Can you say once again, just to
Sure.
the P of X given Z? So basically it's the, because, so this is what you get when you draw once you choose Z, the decoding.
Correct. Correct.
Then you are conditioning on which Z you pick. So you randomly pick Z and then you look at what you get out. That's the first part. The second part is the KL between the distribution of Z given X and the actual real distribution.
The actual PZ distribution, which we defined as the Gaussian, the isotropic Gaussian. This is the isotropic Gaussian. N01, N0I. This is all those mountains that we talked about.
P of Z is given by you.
Yes, P of Z, we don't know. We assume it to be this N01. Remember, we made this design choice.
So in the first step, we are doing marginalization, right? So we can choose any PD we want.
Any PZ I want.
And then I choose to marginalize over isotropic Gaussian.
If you choose that.
Yeah.
Okay. So this is what your encoder learned. This is what your decoder is doing. And you train the VAE to maximize that lower bound. This is what actually a VAE does. And now we want to say we'll do exactly try to do this math, but not for one encoder, one decoder. We will do it for a series of encoders.
Sorry, so you said the QZ given X is what the encoder is.
Correct.
Okay.
Correct. Because QZ given X, remember,
Puts you into this.
what is the, for a given chessboard image, what is the right rule? So we want to derive ELBO for this one. Okay. So to do that, we want to do some basic Markov derivation, which will help. And this is the derivation we want to do. We want to learn the joint probability of x0, x1, x2 all the way to capital XT. Okay. Let's do that derivation. I will be quiet and I'll let you look through it because I think that's easier. Okay? And tell me whenever you want to discuss something. This is the joint distribution of all the variables x0, x1, x2 till x capital T. Okay? This I can write as, remember, there's a law of total probability which says P A B C is equal to P A given PC times P B given C times PC. Okay. If I do that, if I apply that over here, I take x0 given x1 to t, and the remaining is x1 to t. In other words, PAB is equal to P A given B times PB. This is exactly this. Clear? Markov says, if you have the previous step, you can forget all the steps before that. Okay. Can you give me an example of Markov, guys? Something where if you have the previous one, you don't care about the stuff before that. Coin toss. But do you need the previous coin toss to predict this coin toss? So all I'm saying is you need to predict something now. If you know the previous one, you're done. You don't need to know what happened yesterday before that.
I'm walking and no one's asking me my current location. Just
I'm walking and suddenly you take a picture of me and I'm here. Okay. And you want to estimate what was my previous location. Do you care about, or sorry, you want to estimate my next location? Yeah, my next location. Correct. Right? You take a picture of me suddenly, and then you want to estimate my next location. I could go this way, I could go that way. Do you need my past information? But maybe in this case, I do need, because I need to know the direction. Yeah, I need to know the direction.
I mean, in Markov Chain, it's like you take a photo when you are walking. So it also contains your velocity.
But okay, you're on the right direction, but I'll sharpen this a little bit. Okay. You go for a new job, you change your job. And now you got the job and you're negotiating with your interviewer what is your salary should be. Do you care about the previous job's salary, or all that matters is what your salary now is? You see that? Oh, people saying yeah. But typically you would say, if this is my current salary, I need to be better than this, right? I don't care about the previous one. Here's the last one. I want you to predict where a taxi will be in Manhattan. Do you need the information of the, and suppose I say I'll give you where the taxi dropped off its last passenger. Is that enough for you to predict where the taxi is? Or do you need to know where the taxi dropped the last passenger and the last to last passenger and the last to last passenger? If I tell you where the taxi dropped off the last passenger, you do not care about any of the passenger drops before that. You can predict it based on that. That's Markov. Okay. So in this case, because we are going to add noise at every step, independently of the previous steps, it is a Markov process. Okay. So x0, probability of x0 given x1 to t, x1 to t basically means x1, x2, x3, x4 all the way to x. This is only p x0 given x1. Because p is basically the decoding process. If I give you this, I can denoise from here. I don't care about all of this other information.
So our goal is to reach the state where you have 5 nodes, right?
Right.
And we have n steps. So that means on each step, we must take.
We have T steps, capital T steps.
these key steps, in each step, we need to take some amount of noise towards the goal.
Correct.
So let's say that we're previous to the final step.
Correct.
T minus.
Correct.
If I don't have how many steps I had before, how do I know the step that this is the final step to reach the white noise state?
I am going to add noise to every step, right? I'm going to design the noise in a way so that after you add the noise capital T times, you become a full isotropic Gaussian distribution. So there is nothing to learn in the forward process. Because all I'm saying is take an image, sprinkle noise. Whatever you get, take that image, sprinkle noise. Whatever you have, take that image, sprinkle noise. But I'm adding the sprinkling of noise based on some schedule such that at the end it becomes Gaussian. What we are calculating here is the backward process, P. This forward process is called Q, which is sprinkling noise. The backward process is denoising. And we are calculating the backward process.
We're saying that we don't need to know where we are.
Correct, exactly. Because the denoiser is going to say, if I know this one, I'm going to denoise from here. I don't need to know anything in the past. Okay. So this is Markov. And now this one, you can write again using Bayes rule. Please take a look at it. Let me know if it's not clear. Yeah. Bigger. Any problem? My handwriting is not too good, but hopefully it's okay. Good. Guys, any thumbs down? Good. So we have this for the whole joint distribution, x0 to xt. Now, let's look at this. This is the forward process. So I want to estimate the joint distribution of 1, 2, 3, 4 all the way to t given x0. Cool. That's what I want to calculate. Why we are doing this, we'll tell you later. But let's say we want to calculate this. I see some frowns. What is this in plain English? Joint distribution of all these states given the starting points. Right? Good. This is this. I'll keep quiet. Tell me if this is correct. This one became this one. Why? Markov. So it becomes this. You don't have to remember. Just see, I want to partly show you many of these things. Once you pick them up, they're not hard. Once you pick them up, you can understand full diffusion with full clarity. These are kind of the small toolkits. If you see this and you go away, you lose out all the fun. Okay? There's nothing here, right? Bayes. Pretty much just Bayes and Markov. Very good. Now we are ready to do ELBO for the full hierarchical VAE model. Let's start. Log of px is what we want at the end of the day. What is this? What do you call this? I have only x as my variable. Or let's call this x0. What is that? starts with M. Agree? Now I'm marginalizing with all x1, x2, x3, x4 all the way till capital T. That's why this starts from x1, not x0. Right? This is P x0 and marginalize with x1 to T, dx1 to T. So I marginalize exactly the way I did it before. How do you get this? Variational. I multiply the same distribution, top and bottom. Right? This is 1, right? This divided by this is 1. The same thing. That's the variation. What is this? Oh, if I pair these two, then this separates out and that becomes the distribution. So I can write that as an expectation where I bring this into the expectation. Good. Good. This is, how do I get this? Gen sense. This becomes gen sense. Very good. You're doing great. This have you seen before? Px0 colon T. Hey, we saw that right here. So I plug that over here. This, whatever we got, we plug that over here. You don't have to follow, but just see what it entails to get to the derivation. Very good. Now, okay, now there's a trick. If I take x0 given x1 out of this product, if I take x0 given x1 out of this product, then I can write this as t equals 2 to capital T. True? Very good, that's easy. And similarly, I take xt given x capital T given x capital T minus 1 out of this product, I write this t equals 1 to capital T minus 1. Good. Arithmetic. And now you see, look at this step. This was t minus 1 given t. So this is past given future, correct? I'll write that as past given future, but I'll write it as xt given xt plus 1. This is also past given future. But this t equals 2 becomes t equals 1. Stare at it. Right? Very good. So now I separate this part out into this term. And I separate this part out into this term. Almost there. Guys, this one, now I separate it. Can you tell me what this is? What is x0 given x1? This looks like x given z. In a single VAE, x1 was z and x0 was x, right? So what term is this? This is the reconstruction loss. Because given x1, you have to reconstruct x0. So I have the reconstruction loss term here. Which one?
Index.
This one.
Zooming.
You still have x1 to t given x0. But that is like saying, okay, guys, you need only x1 here, right? So can I simplify this? I know I'm making you go through this. Can we simplify this? Just x1. Because all you need to calculate this term, you just need x1. So why do you need all this 1, 2, 3, 4, 5, 6, t? Just ignore this is x1 given x0. Hey, E of x1 given x0 or E Q x1 given x0, P x0 given x1. Does it look like variational autoencoder? I hope you see this is exactly E, Q, Z given X, P, X given Z. Rule given image, this is your posterior, whatever encoder learned, image given rule. So you sample from this distribution, which is you pick a rule from our moon phase Z points, you pick a rule, you give it to the decoder, decoder gives you X. And because this is part of the lower bound, when you maximize the lower bound, you want to basically maximize this probability, which is the same as reducing reconstruction error. Very good. So first term is reconstruction error matched with VAE. Okay. Second term is this. Okay, let's look at the third term first. Yeah, let's look at the third term first. Does this make sense? Can someone tell me why it makes sense?
Linear.
Just linear. What is linear? True. Expectation of A plus B is expectation of A plus expectation of B. So you can sum that up. Very good. Can you now go from here to here?
You only need XT.
You only need, this one has x1, x2, x3, x4 all the way till xt. What all does this need? It needs xt, xt plus 1, xt minus 1. So you don't care about the other xt's, right? So you make that x1 to t, x1, xt minus 1, xt, xt plus 1 given x0. So that's a simple move. Very good. So we are done over there. Can you go from here to here? Same thing. X1 to t, you just bring it down to whatever you need in this equation, xt, xt minus 1. So you just write xt, xt minus 1. Okay. Now comes the main trick, which is basically what makes all of this happen. Do you see how to get from here to here? Let me say this. KL. What is KL in plain English? What is KL divergence in plain English? Distance between, divergence between two distributions, P and Q. The equation for KL is you take samples from P and you do the ratio of log P and Q. This is KL divergence. This is a little bit tricky. This
no, it's Q by B, log Q by B. KL is Q by B.
no. So this is an expectation, right? So if you write this as an integral, this will become the distribution. True. Expectation x coming from fx gx is the same as integral. Anyone wants to take integral what? So if that is true, then I can write this as integral log of that times q xt minus 1 xt given x0. Agreed? Okay. This one now I can write as q xt minus 1 given x0 times Q xt given xt minus 1. And this Q xt given xt minus 1, I take inside this. If I take this Q xt minus 1 inside this, this becomes expectation that becomes scale divergence. Okay, not important. But all I'm saying is this is all it takes. You need to understand KL divergence. You need to understand base Markov, your set. You can do many things with that. Very good. So I'll just skip and I'll show you that the final ELBO becomes this. And let's look at it. Let's look at what it means in plain English. Okay. What do you have the laser pointer? The first term is what? Reconstruction. X0 given X1. Second term is what? Yeah, it's on this. Oh, okay. Second term, what is this saying? What is P of X capital T? What is X capital T? The last step of the Markov, right? That's X capital T. What is the probability of that X capital T? Gaussian. 0, 1 Gaussian. So this you know. And what is this? Xt given xt minus 1. So if I give you some xt, sorry, I give you some xt minus 1, you're saying what is the distribution of xt if I give you xt minus 1? What is that? If I give you xt minus 1, how do you go to xt? By adding noise, right? You have xt minus 1 is a picture. To go to xt, you just sprinkle noise on the picture. So qxt given xt minus 1 is a Gaussian. So this term is saying, hey, you better make sure that at the end step, which is qxt given xt minus 1, this distribution exactly matches an isotropic Gaussian. Right? You're noisifying the process, you're noisifying the image. The last point of your noisification has to exactly give you a white noise. Correct. So this is always 0. It'll always be 0. Exactly. But one subtle thing is there. At every step you're adding noise. But it may not be that the final step becomes a 0, 1 Gaussian. Right? You add some kind of bias. Yeah. You have to design it to make sure that that is N01. Perfect. And what is the last step? What is this, guys? P theta, which means going backwards, xt given xt plus 1. What would you call that? Give it an English name. P theta means you're going backwards. Xt given xt plus 1. So given this, you're getting this. What is that? Denoise. Right? So this is the denoising. A neural network that's going to learn to denoise. Right? And what is this? Noisifying. So Q is noisifying, P is denoising. So look, the ELBO now essentially says you have to make sure you have to reconstruct the original image. That's your first goal. Second goal, tell me in plain English. Second goal, your last one has to be a 0i Gaussian. You have to make sure that. Like, these are the things you're telling the neural network. If you make sure all these three, you'll be able to do generative models. Right? So this one is saying your last state has to be a 0i Gaussian. And what is the third one saying in plain English? Your encoding process, that's a Gaussian, and your denoising process, we don't know what that is. That's a denoiser. These two should match.
But should be Gaussian as well, then if you want to mix them.
But you can do two things. One, you can force it to be Gaussian, or you can do a few other things to make it a Gaussian.
So you say train, these going to end up with Gaussian.
Because we are going to do a little bit of massaging. Yeah, we will, this one, we will treat it as a Gaussian, and we'll try to match both of these. This one that we learn, we will try to match it with this Gaussian.
Is it like P is the one you learn?
Correct.
Is the training process going to end up making it Gaussian?
No, you're going to model it as a Gaussian, and you're going to say, hey, neural network, learn the mean and variance of this Gaussian. Good. Now, let's look at formally what the encoder is doing. This is qxt given xt minus 1. This is a noisifying process, right? This is a normal distribution. Is this clear? This is saying, if I give you xt minus 1, which is an image, you multiply that xt minus 1 with some square root of lambda, there's some scalar, and you multiply and you use a variance of this one, and you add a noise using this mean and variance. This is telling you the distribution of noise that you're adding to xt minus 1. Okay? So every step is a noisification process. This is the last thing which is going to be heavy. Given the past, the next step is a Gaussian, because every time I'm sprinkling noise. Now I'm asking you, hey, can you say something more interesting? Which is, what is xt given x0? I give you the initial image, the clean image of a cat. Okay? And I've noisified it multiple times to make it xt. Can you tell me some relationship between xt and x0? Any thoughts?
Gaussian, keep doing that.
You first added some Gaussian, and then whatever is the result, you add a Gaussian. So you can think of it as adding Gaussian noise plus Gaussian noise with some weights. And then you again add Gaussian. Gaussian plus Gaussian plus Gaussian, if you do this independently, is a Gaussian. Right? So it's interesting that the Tth noisified image is actually the original image noisified with a large Gaussian variance. Right? So every step, you don't have to think of it as, oh, I noisify the image, and then I take that image and I noisify, I take that image and noisify. I don't have to do that. I take x0, I noisify it with a little bit of variance, that gives me x1. I noisify that x0 with a larger variance, gives me x2, x3, all the way till x cap. Make sense? Hey, do you see deja vu? When we do Langevin, we're going to noisify with a larger and larger variance. Good. So this is sum of Gaussians, and this will prove to be a Gaussian. And if it's a Gaussian, then that's great, because every intermediate point given x0 is a Gaussian. And that's beautiful. Good to have that property. Okay. The last thing that we'll do is there's a problem here. The problem is the following. Look at this term. I am drawing samples from this distribution. Agree? Can you tell me how many dimensional is this distribution? How many dimensional is xt minus 1? 4,000. How many dimensional is xt plus 1? 4,000. This is a joint distribution. So if you pick a sample, which is basically xt minus 1 and xt plus 1, together, how many, what is the, over what dimensional space is that distribution? 8,000. Okay. So now you're sampling not from 4,000 dimensions. You're sampling from 8,000 dimensions. And in sampling theory, the more the dimensions grow, your variance of sampling grows very large. This is a bad thing. If you have this term in your equation, it's bad. Because the variance of those samples will grow large very quickly. We want to massage it. We want to change it. And this is where this is pure mathematical people know how to do this very well. They will massage it in a way that will become complete. Okay. So 3 more slides, Yulin will take over. 3 more slides that will show you how to massage it. And that brings us to a beautiful, beautiful form that will completely explain it. You can use that term.
Yeah. Okay. So remember, our goal is to take these distribution xt minus 1, xt plus 1 to only depend on one distribution, one variable, right? We hope it can be only single variable, like here, qxt given x0. So our job is start from here. We go to here. You can see we only need to sample from qxt given x0. Okay. But before I want to emphasize on what Ramit was saying, if we look at this noisifying the noise process, we are matching which arrow? Xt given xt minus 1 is this arrow. Right? This is where we make a noise. Xt given xt plus 1 is which arrow? It's this arrow. Hey, it's a little bit counterintuitive, right? Because hey, it's intuitively is that if I noisify from xt minus 1 to xt, I should match the distribution from xt back to xt minus 1. But no, we are saying this term, consistency term, is actually matching here. This the previous steps noisifying process to next steps the noise process. And why is that? Because through the because we separate the previous 2 term out, which is the reconstruction error, this error, right? Reconstruction error is saying that, hey, I want to estimate x0 from x0 given x minus 1. And the KL divergence term, your final prior matching term. So if you take this arrow out and the last arrow out, how can you do match? You will see, hey, actually you need to match these arrows shifting in T. And I mean, in a high level, that's why you need to have xt minus 1, xt, and xt plus 1. It's all because we want to separate out the reconstruction error and the prior matching term in order to train the neural network.
Actually, I never thought it that way, but good, thanks for the point.
Okay, then now I'm saying no, because statistically, this guy sampling, knowing I need to sample these 3 nodes. That's too much. I mean, the variance is too much. I found that if we train the noise, you actually, you can directly train a diffusion model like that, but it will be very hard to convert. You need like millions of images to converge. So now we do a trick, and now you can see that we will not get into a detail. We directly tell the truth, but I will tell you what is the trick. The trick here is we substitute all the ELBO term before. We have this term, xt given xt minus 1. Now we substitute with xt given xt minus 1 and x0. You can see that these 2 terms, based on Markov, they are equivalent, right? Because we say xt only depends on xt minus 1. Even if I give you one more term, the probability will be exactly the same. But with some probability massaging, later you can somehow take this x0 out, and then you can have a term of xt given x0. You can see here, xt given x0 instead of xt given x1. But I mean, I will not go into detail because basically that's some substitution of variables.
Yeah, it's not complicated at all. You just massage, you just substitute variables in the right way using Markov, right? And you arrive at this.
Yes, and you are interested. If you are interested, we would refer you to read that diffusion paper. But it turns out that we can turn the term ELBO into the noisy matching term xt given x0, but at the cost of, you can see before is qxt given xt minus 1. Now it's qxt minus 1 given xt and x0. And the later term becomes it stays the same.
Why do you need X0 here? It's Markov as well.
Markov is for q is xt minus 1 t given xt minus 1 t.
It's that way.
It's the backward, yeah, backward. So now we can, next slide, we have the picture and we can see it better. Now, let's see, why do we need xt given x? Why do we need two terms here? You can see, to know xt minus 1, to know this node, I'm telling you I need xt. But that's not enough for noisify. I also need to know the original image because xt minus 1 given xt, it's not Gaussian.
It's not Gaussian.
It's not Gaussian. Okay. So that's why.
Important. This is important, right? Xt minus 1 given xt. Is that Gaussian?
Xt minus 1 given xt. I give you a noisified image. And then I'm asking you what's the original image.
That's not Gaussian.
That's not Gaussian. That's a kind of an inverse of noisify, right? Okay, now let's look at this term. Yeah, thanks for asking the question. So this special term, is it a Gaussian? We're asking you what is this distribution? And now if we take Bayes rules, xt given ba given b, b given a, right? You can see that it's all conditional x0 and qxt given 1 and qxt. Now let's write out what of each of the equation is. The first term qxt given xt minus 1.
Wait, stop. Is that Gaussian?
Yes.
Now it's a Gaussian, right? Because
Qxt given xt minus 1 x0. Why is it a Gaussian?
Just some Gaussian.
It's a sum of Gaussians.
no. It's because it's a noisified process, right?
Qxt given xt minus 1 x0. X0 is superfluous. Xt minus 1, if you know, you can noisify and you can get xt. That's a Gaussian.
Yeah.
Right? Good.
Now, what is if? So we already know that. So this is a noisified process. It's a Gaussian, and we even know the parameter of this Gaussian, right? It's 1 minus alpha t. That we put some variance there, identity scale of identity variance, identity matrix. And now let's look at the denominator. Xt given q of xt given x0.
What is xt given x0? Q.
It's Gaussian, but now that's because sum of Gaussian. That's the reason, right? So xt given x0, we already derived that. Ramin already derived that. It's sum of Gaussians, and even again, we can write it out its equation. It's an analytical expression. So it's based on, I mean, in each steps, how large you are going to noisify your image. So here you have the mean of your variance of all these steps. Now, this term, qxt minus 1 given x0, is this a Gaussian? It's also a Gaussian, right? Because the same, it's also sum of Gaussians. So we can write
Whose variance is higher? Qxt minus 1 given x0 or qxt given x0? Given qxt given x. That variance is higher. So one is a more noisified image, one is a slightly less one.
So we also have this Gaussian like this. Now, if we look at this equation, it's a Gaussian times a Gaussian divided by a Gaussian. And if I'm not giving any assumptions, this probabilistic is not guaranteed to be anything. But under some constraints, one of the constraints is that, hey, your covariance matrix is always diagonal because you see, right? It's an identity matrix times a scalar. As long as your covariance matrix is diagonal and under some small constraints, this guy can be a Gaussian.
I think, and this is something I'm not 100% sure, I think this also makes an assumption that t plus 1 and t cannot be big jumps.
Yes.
You need many t steps to go all the way to white noise. If you take big jumps, then I think that assumption fails, not 100%.
So why is it not a Gaussian? I mean, each of these is e to minus, variance x or so. You just multiply and divide, effectively take these x terms and sum them up together. That should be a Gaussian as well.
I think the normalization term doesn't work out.
Okay, so if this is a Gaussian under some mild assumptions, then we can look again into what is the mean and variance of this Gaussian. And it turns out to be, after some massaging, you can see that it can be right here, written out in this expression. Let me enlarge that. I want to mention two things that worth your attention. First, let's look at the covariance first. The covariance is not dependent on any of the image. Quite intuitive, right? Covariance is your covariance matrix is still an identity times some scalar, and this scalar is not dependent on your image. Why? Because it only depends on how much you add your noise, and then this this comes to your variance. Note that you can see, right? There are some images term kicking in, but the distribution comes out. Still, the variance is not correlated with your image. And that's the first observation we need to remember. The second thing, in terms of mean is the weighted sum or weighted average between two terms, xt and x0. And then they time it, so you can see your mean is xt times some weight. You can think of this is the weight of xt. And this is the weight of x0.
You missed the term, but that's fine. You missed one.
Oh, yeah. Sorry, this is a weight for x0, right? So two things. Mean is the weighted sum, and your variance does not depend on x0. Now, with that, we are happy. Because note, we only need to sample from xt given x0. So we only need to sample this term, this node. And then we are matching pxt minus 1 given xt, this green arrow, with the pink one. This pink one is saying, hey, I need xt, right? That's where you are sample. But I also need one term, which is x0 in my condition. Okay, one quick question. Hey, then why do I not sample x0? Because here it's a condition. Why I don't need to sample x0? That's a tricky. Any thoughts? I condition on x0, but why I don't need to sample x0? Because x0 is given. Remember, in the full diffusion, you always have your image as your input. You want to train on that. So your x0 it's a delta function. It's just there so that you can use x0 anywhere without sampling that. You can see that here you also have x0. Okay, now we are happy. Why? Because instead of matching xt minus 1 to x0 with xt plus 1 to x0, now it's all depends on xt to xt minus 1, right? So you can see I match this green arrow to the pink arrow. Except this pink arrow has a small term, which is a look ahead term of x0. Now, one step before I will show you the intuition. But if we want to learn the p xt minus 1 given x0, do we need to learn the full distribution? No. Why? Because we already showed this is a Gaussian, right? We already showed q xt minus 1 given xt and x0 is a Gaussian under some mild assumptions. Now, we can estimate the mean and variance of that. And more than that, we know that our variance does not depend on x0, any of the x. The variance does not depend on image. Remember what we see in the Gaussian slide. So that our neural networks only needs to know the mean, learn the mean. and the mean is actually the weighted sum between xt and x0. He needs to learn that weight between xt and x0. Okay, now our neural network only needs to learn the weight or the mean between xt and x0 to construct xt minus 1. In plain English, what is that? In plain English, what is that? I give you some noisy image. I give you a clean image. Now I'm asking you, can you give me some less noisy image in between with weighted average of these two? So you know, diffusion denoiser is actually doing what? He takes the x0, he takes xt, the noise by image. He wants to learn the weight such that I can reconstruct this less noisy in image.
Yeah, good, good. So imagine that your home is in Urbana-Champaign. Imagine. I noisify your home location and your noisified home location is DC. That's it. Right? This is the noisification process. Right? Your denoiser is now saying, okay, given that I know your starting location is Urbana-Champaign and your noisified version is DC, if I want to denoise it one step, which way should I go? And what you should do is, from DC to Urbana-Champaign, you should draw a line and kind of go in that direction. That's denoising. Right? Because the fact that you came from Urbana-Champaign to DC, my noisification, you must have come in some route that goes through Ohio. Geography is not great. Pennsylvania. Anyway, so I came through that track to land at DC. And my denoising is, you know Urbana-Champaign, you know DC, just go back one step.
So how does it look on inference now? Do I have an x0 when I start inference? I'm going to do what?
This is when you're trained.
This is when you are trained. Yeah. So remember, you want to maximize the ELBO, and all this happens when you are doing training. In inference, you do not have any like all of these terms because in inference you don't know what's the x0, so you cannot calculate reconstruction term, all these things. But hopefully, once you match your neural network with this cube, later during inference, it will generate a reasonable image.
So when you do training, if you give an x0, you calculate, you have an xt and you want to find xt minus 1. So that means that you find the, as you said, the linear condition. Right?
Yes, correct.
And then you update the weights of that denoiser with that new one, or is that how the training?
No, you tell the neural network, I give you 1 million pictures. For all of them, I'll also noisify them and give you 1 million white noise. You learn one neural network that will take all of these 1 million points back to the picture. So you have to learn a common neural network, theta, that will work for all of them.
Yeah. So one thing, I mean, implementation detail. In practice, we are going to use one neural networks to model all of these denoising process.
And not only for one image, for 1 million image.
Yeah.
But your denoising process just Gaussian, so you can
Just Gaussian.
Yeah,
It's only learning the mean.
you're only living, right?
Yeah.
So that's just one number.
Just one number.
Just one number.
But you will do it across all capital T steps and all images.
No, it's one mean for each image.
One mean for each image. For every step.
Yes.
So capital T times the number of images. That's what you have to do.
I mean, theoretically, you have 4,000 mean for image. Yeah, because you have 4,000 dimension. Yeah.
Just for one step.
That's just for one step. Yeah. Yes.
Oh, that's a good question. But look at this sum. T equals 2 to capital T, right? So all of this except the last one. Because the last one we've already taken out and said that's reconstruction.
But I mean, for the VAE, I was learning one function that was converting from the starting point to the latent.
Right.
Yeah.
Space, right? That's one function for all images. Now you're saying I'm learning one Gaussian for each image. So how do I reconcile these two ideas? Like there, I had like one.
No, but here you're not learning the latent space at all. This is given.
Sure, the back.
The back, yeah.
Your decoder is doing all the way back. is doing all these works.
But I can't have one decoder per unit. You have one decoder for all.
Yeah.
That I can't.
Yeah, that's why the model has to be very big. But the model is learning that one decoder is going to learn if the pattern is the hazy pattern looks like a ball, then I need to go towards the ball. But if the hazy pattern looks like a tree, I need to go towards the tree. So one neural network model is learning that. So that same model is learning from noisy, rough patterns, which direction should I go that will give me a realistic image. That's why you need the model to have high complex, high model complex.
The model only learns the direction, or it learns also the magnitude of the noise pattern. So how much noise will be moved? Because I assume here you have a set, big set of steps.
Yeah.
Right? And each time you're learning the denoise part, you take a specific step.
Okay, so about the step is actually the variance, right? So recall we were saying the variance is not dependent on the variance is not dependent on the image itself. So in practice, once because when we are noisifying, we define in each step how much noise we are going to add. In denoising, actually we will plug this parameter back to the denoiser.
So the short answer is direction.
So denoiser only need to output a unit vector saying that, hey, go this direction, but how long you should go, we will tell you.
Variance.
Decided by variance, and we can compute that analytically.
Because remember, right? From where you came to DC, that variance is known. Because that's a function of the noisifying process. Right? So from DC, if I need to figure out where I came from to DC, I just need to know which direction I should go back. Because from that direction, the variance is known of how much I came.
Yeah. Is there another algorithm where you find the number of steps plus the variance of the whole process? Or
This is a design choice, and this is where things are becoming interesting in advanced, just current literature. Today, that capital T has to be 10,000. Because this is a stochastic process. Okay.
What is this depend?
Okay, there are some assumptions where like you know, right? This qxt minus 1 given xt x0, that is a Gaussian only when those jumps are small. You add noise in small steps. If you add noise in big steps, those assumptions fall apart.
So this isn't dependent on anything, but has to do with payments.
Sorry?
The number of steps is independent of anything to do with it. So for example, the resolution is independent of the steps that you're.
Normally it depends on the dimension.
Yeah, it depends on the dimension, right? And also, it depends on how close. Sorry, can you give me the pointer? The more T you have, the more this will look like a Gaussian. Right? Because we made the assumption that this is a Gaussian. But if you take 5T, 5 steps, and you go to white noise, this is not going to be exactly.
But if you take too many steps, there are down.
No problem. Just
So
time.
it-
Just time. But let me just give you a pointer. The state of the art in diffusion is what's called DDPM. If denoising diffusion based probabilistic model until 2022. And they model this whole thing as a stochastic differential equation. So the solution of a diffusion model is the solution of a stochastic differential equation. Okay? You don't have to understand what that means. But the beautiful thing that happened last year was they said, oh, you don't need a stochastic differential equation. You can model this as an ordinary differential equation. And that makes things much simpler. And that the implication of that is instead of capital T being 10,000, you can now make capital T 500. Accelerates everything much more because there's no stochasticity. You're not going to get it.
Just want to do an analogy of from DC to Urbana. Think of this. So different steps is like I'm constraining you what you can do. So I'm asking you from DC to Urbana, you can only take plan. Compared to you can walk or you can drive a car. So plan, if you need to take an aircraft plan, that means every time I need to do a big step. So I have to plan my your denoiser needs to be or your planner needs to be super accurate. Otherwise, you might go to I don't know, Los Angeles and need to fly back because you are taking too big steps. While when you are doing car driving, you can do small tuning during. Okay, you miss this you miss this intersection and then you go next. Okay, I think I'm finishing my part. Now the last part is if we are asking our denoiser to output the mean, let's call it mu theta. We only ask it to output the mean, right? So what does this really means? What does this mean really means? Okay, let's see. We know that we know this term qxt minus 1 given xt and x0. It's a weighted sum between xt and x0, the later term, this one. Okay, mu q is here. Now, our mu theta here, the denoiser only gets access to the noise image. It does not have an end goal. So what can you do? You can think of, hey, how about denoiser will say, how about I guess your terminal, I guess your final, I take a guess at your final image, which is x0. So you can see the first term is the same. Why? Because I have xt, I can do exactly the same weight. I can learn exactly the same weight. But the x0 denoiser is going to guess a clean image based on the current noisified image at xt. So from here, it ends up that I will guess directly what x0 is, and then plug it back here, so that these two terms are matched.
I think I have an analogy right now. I'm in DC. That's noisified. I know that I started at Urbana-Champaign. Now the denoiser has to guess what was the previous hop from which I came to DC, correct? Right? That's the denoising part, right? There is one thing I can guess. Instead of guessing the previous one, I'll guess where I started. Okay? So I guess I started at Chicago. But if I get that guess from Chicago, how I should add noise, that is known. Right? So if I guess correctly Urbana-Champaign, then if I add noise to Urbana-Champaign, I should come to the location from which I came to DC. Does that make sense? Guessing the previous step, say I came to DC, what is the nearby area? New York, let's say. I came to DC from New York City. That's what the denoiser is trying to guess. That's one way of guessing. Hey, where did I come? What can be a short flight nearby? Maybe New York. Another way to guess is, I'm not going to guess the New York area. I'm going to guess where did this guy come from. And suppose I get it right. I guess Urbana-Champaign. Then, once I do that guess, I can add noise. And that noisification I know, right? I should get to New York.
Remember,
so 1 second. So guessing the previous step is the same as guessing the original, the equivalent, because original to the previous step is a known noisification process.
yes.
That's exactly where it doesn't work accurately. The noisification process might bring you to something different from New York. You're absolutely right. But that is why ordinary differential equations makes it deterministic. Stochastic is not going to give you the absolute correct.
Okay, so if we plot this back, you can see that if we consider denoiser as estimating the original image, we take out x theta and x0 out. Then it's so basically the denoiser, you can design the denoiser such that it only gets the terminal image, the final image x0 from every step. From every step. So from t equals 100, I guess what is x0. From t equals 200, using the same network, I'm asking you to step to 200 steps back to x0. So this t, of course, this t, small t is given to neural network. So the denoiser is taking two terms. One is the noisified image at t equals 100, and then the t value 100. Then I ask you to predict the clean image x0. Again, the same neural network, I give you the 200 step tx 200, t equals 200, and then I predicts the clean image. It's equivalent to optimizing this term.
Guessing where you came from to DC is equivalent to guessing where you started.
Yes.
Because where you started from, you can add noise and come back to your previous step. Stochastic.
Maybe a silly question, but what is theta here, mu theta?
Oh, theta is your neural network parameter. So we put theta, mu theta or x theta, just to mean that it's trend, meaning that your denoiser needs to learn this parameter. So for all the variables with underscript theta here, it's all denoiser needs to learn.
So you need to learn
Mu, and or you can learn the image that is x theta, meaning that it's a prediction from the denoiser of the clean image.
so say the x hat theta and so on is the neural network, and theta are the parameters neural network.
Yeah, exactly. You can write this as x0 hat, but we are writing as x theta hat just because x0 hat, x not hat is parameterized by the denoiser.
So your neural network has two inputs like these, which state you're in,
Correct.
what's the value, and you have to guess how to denoise the next
The
step.
neural network has two inputs, the T and the noisified image at T. Those are the two inputs in the parameter. Just zoom in, which is xt and T. Those are the inputs to the neural network. And the output of the neural network is guess x0. Yeah. Image, show the image.
I guess I have a question. Where we are coming from DC, you have to ask that direction. For example, in a 2D case, suppose you are in one location like DC, and, let's say we have 360 directions you can go from. Right?
Yeah.
Maybe 10 of the locations are nearby locations, and you can like choose them correctly. Then the probability will be 1 over 60. Well, 1 over 36. 36.
Yeah.
How do we make sure? I mean, the more step you take this right direction, the probability of this right direction will increase. How do we make sure this neural network works? The more gas you take is, for example.
But the more guesses you take, the less mistakes you make in each guess. If I take small steps, let's say my step is every walking step that I'll take. If I make a mistake, the next step I can correct it. And the neural network will say, how should I walk? Small steps. Because eventually it has to come back to x0. So it cannot diverge, right? Because you know x0. Go, keep on. You finish it.
Okay, let me finish. Okay. So this we now know that this denoising matching term is nothing but asking a denoiser to predict the original value, right? The original image. So that is saying, if I'm giving you x capital T, I ask you to predict in the training set. Given x capital T, I ask you to predict the original image, and also x 200, I ask you to
T minus 1.
or xt minus 1, and then I ask you to predict x0, all the way till x1 with only small error or small noise added. I ask you to predict x0. So this is when training. Because I have this x0, so I have this very clear image. You need to compare you input this to denoiser, and then compare denoiser output with this clean image. And you do this for all the time steps.
Hey guys, so what is the thing? You see, right? You're showing examples to the model of what a picture looks like as you destroy its structure. Right? You're destroying the picture structure And you're saying, this is a destroyed structure of this image. This is a slightly less destroyed structure of this image, and so on. And you do this for 1 million images. The neural network is starting to learn, when I see some destroyed structure, I know what kind of image to go to.
So just to give you some intuition is that, you remember Ramesh says that at a later stage, we destroy the semantics, right? We destroy the big picture. So neural networks needs to know, okay, give us these like a face-like image, I need to reconstruct it to a realistic face. Or in a previous stage, we add slight noise, right? So there will be only some dot noise on these people's eyes, mouth. When I see these dotted noise, the denoiser also learns to know, oh, okay, human lips will not have dots on that, so I should remove that, right? So denoiser needs to will learn multiple tasks during this training, from semantic to realistic. Also learn how to remove small defects inside the clear in the noise image.
This is training.
Okay, now,
Well,
yes.
maybe just to repeat, so basically you give me an X0, give me this picture, and then I calculate the error.
Yes.
Then I'm doing my gradient descent training, whatever, on the X theta function, right?
Correct.
Yes.
And I'm looking at the gradient of that error function.
Yes.
And I'm updating my function based on this. And so alpha t is going to be larger when t is larger, correct?
Yes.
So the error is going to be bigger, but then this, or the other way around. So my gradient is going to play smaller impact in the overall chain.
Correct.
Yes. Yes. Yes.
But your total loss is going to be the sum of all the errors from each of those steps.
Each of the steps.
And you can also choose to have, because you have your alpha t's, which is your noisy schedule set, right?
Yeah.
And you can have multiple different samples of the noisy processes.
I mean, current DDPM, we sample only one at each denoiser because you already have 100 million, so you already have statistics there. But I mean, if you want,
you can do more.
yeah,
Every image you can sample 5 packs.
yeah.
Yes.
Okay, in inference. Now that okay, in inference, because we do not have the clean image again.
One second. Hey, what is inference? Now you're telling the neural diffusion model, hey, generate some new images. I'm not giving it any image. Generate some new image. And it better generates a sharp, crisp image of a face without my eyes being here. It has to generate a perfect image. Right? No X0 anymore. So you start from the noise, white noise, and you now need to generate properly. This is how you generate.
Okay, so let's look at this Lena. So assume this Lena picture is not there in our training set. Now we give a random noise, Gaussian noise, to a denoiser and say, hey, this is X capital T, and then we put this small t as capital T. We ask it to estimate the original clean image. It will not do a super good job at the first time, right? Because I'm asking you to predict capital T sets super far away. So you can see, although it's predicting the clean image, this image is still, there are some defects, there are some blur areas, not good enough. But what we can do is from this estimating X0, we add noise, T minus 1 step, capital T minus 1 steps, and going here. Okay, so this X0 hat or X theta hat, we noisify it again, T minus 1 step, big T, capital T minus 1 step. And then we got a noisified, but not random Gaussian, right? You can see slight contour here. And then we put this to decoder once again. We ask the decoder, hey, now I have a not so bad, I have XT, capital T minus 1. And then go back to X0. Now comparing, so the denoiser will denoise it again. Comparing these two, which one denoiser is doing less job? From capital T to X0 or capital T minus 1 to X0? Which one denoiser is, which job is easier? -1, right? Exactly, because I'm putting less noise. So hopefully it will get into a better image, which will be better than this one. And then again, I noisify capital T minus 2. It will give me a better job. I do this T times until I get it from this from X2 to X0. This is already very good because if I have if I have an image, only add 2 times of the noise, it should be quite clean, right? So I use X2 to estimate X0. Now I give it saying that, hey, this is X1, estimate X0. So it will give me a very clear image because now you only need to do 1 step denoising. Yes.
So the backward process is done using your neural network by supplying first the XTN, the number T.
Yeah.
And then your forward process is done by Gaussian.
Yeah. Yeah, Gaussian. You just noisify it.
Yeah.
True or false question. Did you finish? Suppose I pick this white noise picture and I arrive here. And I pick it again. I pick this white noise picture again. And I run the diffusion model again. Will we arrive here or will we arrive at a different? Because
There is noise
this, okay, from this one will we arrive here at this exact picture or not? No. This one, if we give this picture as input, which is X capital T and capital T as input, this neural network is deterministic. So given that input, it will give that output. So it will give this output. But then when you noisify this, that is stochastic. So this will bring you somewhere maybe here. And then when you give that input to the neural network, it will bring you somewhere here. And you do a different one. And you might end up in a different picture altogether. That's the generativeness. Every time you do the same thing, even if you start from the same image, you'll get a different picture. If you start from another sample, which is also white noise, you're likely to get a very different picture.
And why do you not have the modality gap problem? Like the DOEs?
Why do I, what the question is, why don't we have the modality problem?
Which is the modality gap problem?
Yeah, the one where you.
Oh, you mean prior whole problem. Yeah. So, why do I? The question is, where does the prior whole problem goes? Recall the prior whole happens when the KL divergence is a little bit larger, meaning. Sorry.
I understand the process now. Why start with white noise and all? Why don't I give it an image? I can just take this picture and classify it and start with. I can skip a bunch of steps here.
Sure. So if you give that image, you're unlikely to deviate too much from that image. Do you agree?
So it depends on how far that path I am.
Oh, so you take that image and you noisify?
Maybe half as a step.
Sure. This is called inpainting.
I can save a bunch of steps.
So this is exactly the application that's very popular now. In fact, don't even think of an image. Take an image, rub off some of it, right? And give that image. So whatever it sees, from that it is going to go in the manifold and so fill it in, right? So matrix completion problems people have worked on with classical signal processing. You just solve that with neural network because you are going to make sure that the neural network is go along that manifold and fill in the parts. So this is exactly called inpainting. It's some form of conditioning, but this is like unconditional.
Okay, and then come back to the prior whole problems. So VAE, remember, we are saying there's a prior whole because there are big gap between a prior big green mountain and small blue mountains, right? And this makes this KL divergence to turn large. And that's why we will have samples of large prior but small posterior. We never seen it in the training data. But here, because we are matching the prior, we force, if you go enough deep, in a large capital T, your prior matching term will be small. It's guaranteed that we noisify. Remember, now we don't have an encoder. We fix the encoder to be a noisy process, right? So the encoder after T step is guaranteed to be very, very close or completely, you can directly say, is an isotropic Gaussian. Isotropic
There's
Gaussian.
no learning, right? Was the encoder's output in VAE was some learned mountain range. Here there's no learning. You know it's a Gaussian. That's it.
Yeah.
So it matches perfect.
Matches perfectly. Yeah. And the denoiser step as well. So it needs to learn from that mountain. And that's why it has much less prior hole problems.
Finish last. This is last line.
Yeah, this is that stuff. Oh, do you want me to skip this?
One question.
Yeah, okay.
So in the inverse stage, why after you inverse is still any noise to it? You cannot directly do this, the left one.
Yeah.
Not to the left one, directly again to the right one. Instead, I guess you're saying we need, after we get to the left one, we need to add noise again.
Yes.
And then to that to the unit.
Yes. Oh, you mean like why don't I directly give neural network this image? Because neural networks might have might make mistakes on this image, and he will never know. Because the neural network you see, right? From, for example, let's say from X capital T to X0. This X0 is not the same or not, it has high error compared to the true image or compared to a realistic image. But at this step, the neural network is thinking that it has reached the goal. From DC, I am saying that, hey, I arrive at my destination is DC. I told you that I have noisified 200 kilometers. I told you I travel 200 kilometers here. Guess my destination. You will say, okay, I guess you are maybe from Urbana. I don't know, 200 might be too less. But anyway, what can the denoiser say without giving any other information? That's its answer.
That's the best guess I have.
That's the best case I have, right? So to give it more information, I'm saying, okay, given you are guessing I'm from Urbana, you are saying, given I'm from Urbana, I will tell you if I'm coming from Urbana, then I will go this way, up to DC. I am going to say I will go take American Airlines and then go to Chicago and then go another 50 kilometers. I will tell you this path, and then you will find me ending at maybe New York Airport. And now you're saying, oh, okay. Now, if you are starting from Urbana, you end at New York Airport. From New York Airport, I can make a new guess because that's that's the only way I get new information.
And another way of thinking about that is the neural network has trained for different levels of noise, right? So for different destruction of the picture, the neural network has trained how to go back. If you just use this one, you're not utilizing the fact of what the neural network thinks this picture will lead to, what the neural network thinks this picture will lead to, right? All this training that the neural network has done, which is basically has understood the structure of noise, right? You're skipping all of that. If you just take this picture and you now give it to the neural network and say, hey, denoise from here. That's because it's determinism. Which one? That direction is determinism. That doesn't determinism. It's not that problem down in there.
There's no probability inside it. Yeah. The neural network is one input, one output.
And I guess the other one other answer that I thought of is your neural network input has to have T. So
Yes,
if you
yes.
directly feed what you have on the left,
You
don't
cannot
know.
fit into the.
I mean,
but
that's
then
a
you can maybe redesign the neural network to say, okay, this one I will fit in something, but the math breaks.
But like different T's, as you said, also
Yeah, exactly.
different behavior. Smaller T, denotes larger T.
So maybe just a practical question. So when I think about X theta, X T of T, the neural network, right? Do I, is it a single network for all steps? Do I train different networks for each step?
One network for everything.
Yeah.
So
So
just an input parameter.
T is just an input parameter.
yes.
Go back one slide. So one network for all these steps.
All this stuff.
Yes.
So you take the neural network.
Not this previous slide.
Previous slide.
Yeah,
So
One network.
one network for this.
So
So you're
I'll act it out for you. I have a picture. I take the picture. I have a neural network. I take the picture. First, I basically noisify that picture into capital T pictures. So I have now capital T pictures. I give it to the neural network, and I say neural network for x capital T, which is a white noise, predict x0. For x t minus 1, predict x0. T minus 2, predict x0. For all the t, predict x0.
But that's a parameter too.
The neural network has a bunch of parameters.
I know, but these are the parameters.
Is also a parameter, but t people would say 10,000.
But why is that? Like, why don't you, from your theoretical model, you could have different functions, right? You don't care. XT is just a function of trait. You could have one network for x t comma 0, x t comma 1.
We have compute, do it.
I see. So it's just the practical.
Absolutely. Already this is super high.
Yeah.
If you want to break it up for different stages, sure, do it. Absolutely.
But I mean, an intuitive way of doing that in one neural network is that you can see that for, let's say, x100 to x0 and x150 to x0, these two neural networks, if you train them separately, there will be a big number of parameters they are shared. From x100 and x150 to the x0, they all need to capture some semantics. They all need to learn how to denoise the defects, right? So a lot of parameters will be shared. So that's why we want it to be a single neural network handling all stages of denoising.
Actually, wasn't that I take back what I was saying? Maybe training one neural network is an advantage, which is the neural network sees for the same picture, what does an XT noisified version and the XT minus noisified version, what is their relationship? You might not have that if you train separate neural networks for each of the steps.
And in terms of how the neural network should look like,
It's a unit. Okay. It's an auto encoder.
So the time index is provided.
The time index is provided. I mean, in practical, it will be a positional encoding, not directly a numerical value, but it's provided. Yes.
Theoretically, the neural network should predict the picture of the previous step, but what actually doing in practice is predicting the picture of the.
No, we said, right, predicting the previous step is the same as
Oh,
predicting the
okay.
first step, because from the
Okay.
first step, you can come back to the previous step
Okay, got it.
by adding ones.
Yeah, and you can see, right, writing code, in terms of writing code, you prefer this thing because you always compare to the clean image. Instead of you have to generate until xt minus 1 and all those things. Yes.
So if you give it the TC, what will it do?
If you give it a clean image, you also need to give it the t, right, small t. But if you give it a clean image, but with, let's say, t equals 10, it means that I cheat you. Hey, this is a noisy image, but denoise it for 10 steps. I mean, if it's doing correctly, it will sharpen the image. If it's doing correctly, but in some cases, it will ruin the image. So it's undefined behavior.
Think of it this way, right? There's that, if the probability distribution, that pretty clean image is already near the high probability value, right? And Langevin would kind of say, oh, from here I need to go. So it's going to take some steps around in that region and give you another image. And that is likely to be similar. It's not going to do much.
Because of the schedule, like at the end, when your T is very small, you can't move anywhere.
Can't move too much.
Yes.
Okay. Let's
Yeah.
take a break. And we have a slightly different take on diffusion. And maybe that's all we'll cover for today. We'll still GAN and normalizing approach. So maybe take a longer break, maybe 15. Longer break. And then we'll meet in 15 minutes and we'll do a different